Hello everyone, welcoming you to Shorup's classes, and today we are looking at the General Economics Paper 1 of the IES 2022 and question number 9 and part A of the problem. So consider the first order autoregressive scheme in the general regression model. How would you estimate the variance, covariance, and the autocorrelation coefficient of the disturbance term in the model? Okay, so let's have a quick look at what we can do. So we can consider any general model. As I said, first we need to see the first order autoregressive scheme. So that our calculations are a little bit easier and we are not cluttered with the algebra, let us say I consider a simple model without intercept, just to keep the calculations a little bit on the easier side. That is my And just as a side note, most of you must be aware that autocorrelation is a general phenomenon that is mostly observant in time series data. So I'm just writing it with time subscript rather than the I subscript. So yt equals to beta xt plus ut. Okay, where we are told that ut follows a autoregressive scheme of order 1, which is known as the Ar1 process. And how does it look like? It is basically saying that ut equals to rho times ut minus 1 plus epsilon t, where modulus rho is less than 1. Now this is an assumption so that our calculations then fall in place, and epsilon t follows um, is identically normally distributed with mean 0 and variance sigma epsilon square. Okay, so this is the basic structure that we are looking at for the autoregressive scheme. Okay, so now let's have a look back into the question. So how would you estimate the variance, covariance, and the autocorrelation coefficient of the disturbance model? So when we are talking of autocorrelation, if you look at this equation carefully, the autoregressive one equation is basically saying that the random error in today's time point depends on the previous time point, right? So they are related. So we are basically told to find these things. We are required to find the variance of this, the covariance of, let's say, ut with some past values. So let's say a general lag ut minus s, and we are also told to find how would you estimate this rho, which is the autocorrelation coefficient. Okay, now since today's error is dependent upon the previous period's error, so we need to find the covariance, how they are related. So let us see how we can evaluate these things. We'll go step by step. I'll first start with the covariance term. So understand this. Ut equals to rho ut minus 1 plus epsilon t. This is the autoregressive scheme that we are talking about. That means today's error, the random error, so to say, depends partially upon the previous period's error. And this is the um, way it has been following. So that means the previous period's error, which was ut minus 1, would be depending partly on ut minus 2 plus epsilon t minus 1, right? Fine. This is how it would work. And similarly, so this will make rho square ut minus 2 plus rho epsilon t minus 1 plus epsilon t, right? And similarly, if you ut minus 2 again partly depends upon the error in period t minus 3 plus epsilon t minus 2, right? Plus rho times epsilon t minus 1 plus epsilon t. So what can you see? It will become rho cube ut minus 3 plus rho square epsilon t minus 2 plus rho epsilon t minus 1 plus epsilon t. Correct? And similarly, we can continue expanding this expression without any complications. So that means if you understand what is happening, that all the u terms can be now explored in terms of their corresponding epsilon terms, right? And they are getting added up. So what will effectively ut be written as? It can be basically written as summation um, I running from your 0 to infinity rho to the power I epsilon t minus I. Okay, because if you go on expanding, all the u terms can be written in terms of their corresponding epsilon terms, and the more you expand, you can understand from the pattern that the epsilon terms are going on adding up. So again, in the next step, if you would expand u of t minus 3, you would get something in terms of t minus 4 and the epsilon t minus 3 expression, right? So if you continue to go on for n number of periods behind, then you will get something like this if you expand it throughout. Okay, so that is ut is equals to this thing. Now from this you can understand that it will be easier to compute certain things. So what is the expectation of ut? It is basically expectation of this entire thing, summation I running from 0 to infinity rho to the power I epsilon t minus I. Expectation is a linear operator and rho is a constant. So summation I running from 0 to infinity rho to the power I expectation of epsilon t minus I, right? Now what we have assumed that it follows an independent normal with mean mu and variance sigma epsilon square for all t, right? So the expectation is 0. So this thing is 0. So that means what is variance of ut? It is similar, it is just expectation of ut square, correct? So this is basically expectation of summation I running from 0 to infinity rho to the power I epsilon t minus I, this thing whole square, correct? And this thing can be written as expectation of summation I rho to the power I epsilon t minus I whole square plus double summation I j and I not equals to j rho to the power I rho to the power j epsilon t minus I epsilon t minus j, this thing, right? We have encountered this kind of an expansion when we were trying to derive the unbiased estimator of beta hat and the corresponding variances, right? So basically what I'm trying to do is that, like, if you are having any doubts, then we can have an elaborate video on how this kind of a mathematical expansion works, but for now I think most of you are able to understand how we are going on expanding this. So this thing is basically expectation of summation I rho to the power 2I epsilon square t of I minus 1 plus double summation I not equals to j um, rho to the power I rho to the power j epsilon t minus I epsilon t minus j. Okay, so now if you take the expectation operator, all the row values are known values, so they are not random variables. So this will become summation I rho to the power 2I will remain, expectation taken over only the epsilon term plus double summation I not equals to j rho to the power I rho to the power j expectation of epsilon t minus I epsilon t minus j. Now since epsilon are normally distributed, these terms are 0, this term is 0, and this part is sigma epsilon square, right? So what do we get? Okay, sorry, I have made a mistake. The expectation operator will be no longer here, it's over. So we basically have summation, so the sigma epsilon square term will come out, summation rho to the power 2i. This is what the variance looks like. So this is basically sigma epsilon square, and just putting the i's range once more, rho to the power 2i, right? So if you expand the summation, what do you get? You will first get 1 plus rho square plus rho to the power 4 plus so on till infinity. So this is an infinite GP series with the common ratio rho square. So this will become 1 by 1 minus rho square. So that is sigma epsilon square by 1 minus 1 by rho square, where modulus rho is lesser than 1. And this ensures that the variance of the error term is actually defined. That is what it ensures, right? So we have basically found out the variance that we were required to find out. Next comes talking of the covariance term, and then we will talk of the determining rho. Therefore, just the final answer, variance of ut, which is basically your sigma square, is basically sigma epsilon square by 1 minus 1 by rho square, right? Okay, fine. All right. Okay. So now comes computing the covariance. So we basically want to find out the covariance of ut and ut minus s. So the standard formula for covariance is this, right? Expectation of ut minus expectation of ut, this thing, into ut minus s minus expectation of ut minus s. Correct? This is what it is. Now expectation of ut and expectation of ut t minus s are both 0. So this is basically boiling down to computing this expression. Expectation of ut and into expectation of ut minus s. Correct? So now understand this, that ut, we have already seen this, that it can be written as summation I running from 0 to infinity rho to the power I epsilon t minus I. We just showed this, right? Correct? Now if you just split it up a little bit, it is basically telling you, it is the first term will be epsilon t, the next term will be rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 3, and so on. Correct? Fine. This is how it will work. And so instead of ut, if we are trying to find out ut minus s, what will happen? The infinite GP series will continue, but in place of epsilon t, we'll have t minus s minus I. Right? I hope this makes sense to you. So this is what will happen, right? That means if you expand this thing, what will happen? It will be epsilon t plus rho times epsilon t minus s minus 1 plus rho square epsilon t minus s minus 2 plus rho cube epsilon t minus s minus 3 plus so on to the infinity. Correct? This is how it will look like. Now observe one thing. ut minus s is actually an error that has occurred before ut, right? Because t minus s and s is positive. Obviously, I think you have understood, even if I didn't mention it earlier. So your ut minus s is an error that has occurred before ut. Now, if you look at the expansion of ut, what is happening? It is basically adding over all the epsilon terms for all the previous time periods. That means definitely this expansion of ut minus s, this entire expression is actually there in ut, right? So let's try to figure that out, how we can express it. So ut is basically epsilon t plus rho times epsilon t minus 1. So you're going back the time period. That means a point will come when you will actually reach s time period backwards, right? Correct? And then you will be going even backwards. So this will be rho to the power s plus 1 epsilon of t minus s minus 1 and so on. Correct? This is what will happen, isn't it? Okay. Now try to observe this. I'll just elaborate this a little bit more so that it can be easily understood. Rho times epsilon t minus 1 plus rho square epsilon t minus 2 plus, if you want to have a look at the term before this thing, what will that be? It will be plus rho to the power, whatever you're adding over here, that will occur over here. So this will be rho to the power s minus 1. You have not moved s period ahead, s minus 1, that means you are before. So this will be epsilon of t minus s minus 1, so t minus s plus 1, right? And then you will have this term rho to the power s epsilon t minus s plus rho to the power s plus 1 epsilon. So you have moved ahead of the sth lag, so s plus 1th lag, so t minus s minus 1 and so on, right? Now observe one thing, that ut minus s contains this epsilon terms, epsilon t minus s minus 1 and all these terms, t minus s minus n and so on. That means basically, so to say, um, I can split the ut into two parts, this and this, that I have marked in gray. These are the epsilon errors that are not there in ut minus s expression. So let us say I mention them with b. And these are the terms, because see, from epsilon t onwards till epsilon t minus s, all of them are there. So these are the terms that I think we can mention. Okay, so this will be t minus s. I have made an error. And these are the epsilon error terms. I'm not talking of the rho powers. These are the epsilon error terms that are there in ut minus s expression. So this, let me label it as C. So ut is basically can be written as b plus c. And let's say for calculation, the ut minus s entire expression is a. So what I've basically done is I've basically segregated the epsilon terms on the basis of the lag that we have got. Ut has all the lags that are there in ut minus s. So I've basically segregated the ut expression into two parts. One portion which is C, which contains all the epsilon lags which are there in ut minus s, and the second part is the part B that I've labeled, which doesn't contain the lags that are there in ut minus s. Okay, so covariance of ut and ut minus s is basically finding the expectation of ut and ut minus s. So that is basically finding the expectation of what is ut. It is b plus c, and what is ut minus s? This is a. So this is basically this. So that is basically obtaining the expectation of this product a into b plus expectation of the product a into c. Okay. Now let us have a look at the first term, expectation of the product a into b. Now what is the term a? you do not need to write all the terms. We can be a little tactful over here. So this will be epsilon t minus s plus rho times epsilon t minus s. So the expectation is there, rho t minus s plus rho square epsilon t minus s minus 2 and so on, right? And multiplied by the b term, which is basically epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus dot dot dot, this is not an infinite sum, rho st minus 1 epsilon t minus s plus 1. Okay, now look at one thing. So in order to find the expectation, we'll take all possible products that are there, and then we'll take expectation over each of them. So let's say I take the first term over here, epsilon t minus s, and try to take the product with all the terms of the second term. So that will be expectation of this. Try to understand this. It will be epsilon t minus s into epsilon t plus rho times epsilon t minus s times epsilon t minus 1 plus rho square term I'm not writing, rho to the power s minus 1 epsilon t minus s epsilon t minus s plus 1, right? This is what it will be. And similarly, if you write the second term, everything will remain as it is, and the last term will continue, and this term will go. Note that whenever you're taking, so this will go up till infinity. When you're taking the expectation being a linear operator, you will be taking expectation over all these terms. So this will basically become expectation of epsilon t minus s epsilon t plus rho common expectation of epsilon t minus s epsilon t minus 1 plus dot 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 rho to the power s minus 1 expectation of epsilon t minus s epsilon t minus s plus 1 and all the way till infinity. Note that all these terms are 0 because epsilon t follows a normal distribution, right? So all the terms of this infinite expansion are 0 because basically you are multiplying all the unlike epsilon terms. There is no common element in the lags, right? So expectation of AB is basically 0. That means this part is 0. So your answer is expectation of A into C. This is what we need to find out. So the covariance of ut and ut minus x ultimately boils down to just computing the expectation of this term. That is expectation of the term that I've labeled as capital A, the bracketed expression, and the term as capital C. So let us find out. So expectation of A into C. So this is basically expectation of, so I'm just writing down the A term again, epsilon t minus s plus rho times epsilon t minus s minus 1 plus rho square epsilon t minus s minus 2 and all the way till infinity. And the C term is your rho to the power s epsilon t minus s plus rho to the power x plus 1 epsilon t minus s minus 1 plus dot 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 till infinity, the remaining terms. Okay, so both of them are basically infinite in this sense. So now if you multiply them out, what you are getting, so again you can take this one epsilon t minus s and take it with all others. So this will become, check, rho square epsilon square t minus s, right, plus rho to the power s plus 1 epsilon t minus s epsilon t minus s minus 1 and dot 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 till infinity, right? It will continue, plus take this term, the second term. So this will be rho to the power s plus 1 and multiplying it. So epsilon of t minus s minus 1 epsilon t minus s plus rho to the power s plus 2 epsilon square t minus s minus 1 plus all the way till infinity, right? Now take the third term, which we have not written, so let us stick to that. Observe over here that again, like the previous case, when you take expectation, all these unlike epsilon terms will become 0, right? But note, the expression is not 0 over here because you have this epsilon squared terms. That means every lag that you have over here, the lagged epsilon values are the same, only the row powers are different in both the brackets. You can check. Over in the first bracket also we have epsilon t minus s. In the second bracket also we have epsilon t minus s. We have an additional row to the power s. So when you multiply all the like terms, the epsilons will become squared and they will contribute to the expectation. So I can simply write this. So this will be rho to the power s, expected value of epsilon squared t minus s, plus rho to the power s plus 2, expected value of epsilon squared t of s minus 1, plus your taking the unlike terms, expectation will be 0, so I'm not writing them out. Okay, so this will be sigma epsilon square, and this will be rho to the power s plus 2. This is also sigma epsilon square, and dot till infinity, right? So rho to the power s sigma epsilon square can be common, so you have 1 plus rho square plus rho till infinity. So this is again an infinite GP that we have over here. So that is rho to the power s sigma epsilon square divided by 1 minus rho square. So this is the expression for covariance. That means your covariance between error in period t and error in a lagged period ut minus s is basically your rho to the power s sigma epsilon square by 1 minus rho square, where modulus sigma is lesser than 1. So by using this we can estimate your covariance. And finally the last term that we need to estimate is your autocorrelation coefficient, which is rho. Okay, now there are many ways that we can do in econometrics, basic econometric methods. There are many ideas that are given. I just like to mention one of them so that we can complete. So estimating rho. Okay, there are actually various methods to estimate rho, like iterative methods, nonlinear methods, and so on and so forth. So I'm going to discuss some simple ideas of estimating rho. So the one thing is, let me just write down the model once more. So we have yt equals to beta xt plus ut, where ut is equals to rho times ut minus 1 plus epsilon t. Modulus rho is less than 1, and epsilon t follows the independent normal distribution with mean 0 and variance sigma epsilon square. Now, note one thing that directly you can't estimate rho because UTs are unknown, right? The only thing that are observable is basically your ETs. That is the error in prediction. So you need to use these ETs itself to get to an estimate of rho. One possible estimate will be something like this. One possible, it will be summation et minus 1 divided by summation et square. This basically comes out from the Darwin-Watson test idea that I'll discuss shortly. And another possibility that can be explored is like we'll not get into the proof. It's just important for you to just know that et, the error in prediction are often are mostly consistent estimators of UT. So what you can do, you can simply do the normal regression yt equals to beta xt plus ut without bothering anything, and from there you can obtain your ETs, and then you can perform the second stage where you can regress ET on ET minus 1 and get an estimate of rho hat. This can be other possibilities, and there are many more iterative procedures and all, but that won't be necessary over here, at least for your answer purpose. So the second part I think it will be is more intuitively understandable, where you can just obtain the ETs from the normal regression and use them straightforward to make another regression to have an estimate for rho hat. So that is your answer for part A of the question. How will you estimate your variance, covariance, and autocorrelation coefficient of the disturbance term of the model? Okay, all right. So now let's move on to the next part, part B of question 9. So we are required to describe the Durbin-Watson test of autocorrelation. So part B, we are required to test the DW test. Now first of all, to describe it, let us first focus on the assumptions that needs to be made in order to ensure that the DW test will work just fine. The first thing is the regression model should have an intercept term. I'm just writing in short. The regression model should have an intercept term. The second is the explanatory variables, that is basically the x variables, should be non-stochastic. That means basically they do not have any probability distribution. They are known values. Should be non-stochastic. Number 3. The third assumption would be UT follows an autoregressive scheme of order 1. Now note one thing, the DW test that we are going to describe now is only applicable for autoregressive scheme of order 1, not higher orders. That is, if you remember from the last section that I wrote, UT follows rho UT minus 1 plus epsilon t, where modulus rho is less than 1, and epsilon t basically follows independent normal with mean 0 and sigma epsilon square. Okay, this is important. So now in order to test for the autocorrelation, we first write down the DW statistic that is required, or which is often denoted as D. So basically when you just run the model, you get the error terms. So the DW statistic is basically summation ET minus 1 whole square divided by summation ET square. This is the test statistic that we are looking at. Now if you expand this, there is an interesting observation that we have over here. So this will be summation ET square plus summation ET minus 1 square minus 2 times summation ET minus 1 divided by summation ET square. Okay. Now look at the first two summations, summation ET square and summation ET minus 1 square. They basically only differ by one observation, right? In the first summation there is one term extra, so we can see that they are approximately same because the errors are likely to be very less. So as summation ET square is approximately same as summation ET minus 1 square, what do we get? It will be 2 times summation ET square minus summation et minus 1 divided by summation et square. So this will be basically 2 times 1 minus summation et minus 1 divided by summation et square. So this is basically 2 times 1 minus rho hat, where you can understand rho hat is basically kind of a correlation coefficient between the error terms in the sample. So it is often known as the sample first order correlation coefficient. Sample first order correlation coefficient. Okay, and this was the exact estimate of rho hat that I was talking of in the last section. One way can be to just estimate this term. Now note one thing, that if your rho hat lies between -1 and 1, right? Okay, I should write it a little bit neater. It lies between -1 and 1, correct? That is, so if rho hat is 1, that means the errors are perfectly positively serially correlated, then what will be your d value? It will be basically 0. And if rho hat is equals to -1, then d is equals to 4. That means what we can see is that the range of this dw statistic is actually varying between two limits. One is 0 and the other one is 4, right? So if the value of the d statistic is closer to 0, then you have positive autocorrelation. And if the value of the dw statistic is towards 4, then obviously there is negative autocorrelation in the data. Okay, so now in order to test for the presence of either positive or negative autocorrelation, we need to define two bounds, which is known as the lower bound and upper bound for this test. So now to test, I'm just writing it down, to test we define two bounds. One is the lower bound, which is denoted by dl, and there is another upper bound which is denoted by du. Okay, and these bounds are actually given in the dw tables. As you can see, every econometrics book has these dw tables at the back. So basically you have two bounds. One is your dl and another one is your du. So this is your dl, this is your du, and this, yeah. So now the first thing that we want to do is testing for positive autocorrelation. So part 1, testing for positive autocorrelation. The idea is very simple over here, that if the computed value of the DW test statistic is actually less than the lower bound DL, then positive autocorrelation is present. Positive autocorrelation is present. And if the value of the D statistic is greater than DU, then absent. Positive autocorrelation is absent. And if the value of the D statistic lies between du and dl, then the test is inconclusive. That means we are not sure whether there exists autocorrelation or not. This is actually one of the drawbacks of the DW test. And similarly, for the also after testing for positive autocorrelation, we will now test for negative autocorrelation. Testing for negative autocorrelation. So now, as we have defined the bounds dl and du, we will now define two more bounds symmetrically. So we'll have a bound which is essentially 4 minus dl, and we'll have another bound over here which is 4 minus du. Okay, so if the value of the dw test statistic is greater than 4 minus dl, then negative autocorrelation is surely present. Negative autocorrelation is present. And if it is lesser than 4 minus du, then negative autocorrelation is absent. And if it lies between these two limits, that means 4 minus du less than equals to d less than equals to 4 minus dl, then test is inconclusive. That means if you look at the diagram that I had drawn, if I can just shade it out, this part and this part and this part, if the value of the D statistic lies anywhere in either of these three intervals, then we are sure of the result that we can get by applying the DW test. However, if it lies between the unshaded portions, then the test becomes inconclusive. We are not being able to be sure whether there exists autocorrelation or not, or rather negative autocorrelation. Okay. So now moving on to the last part of the question, which is part C. So given a sample of 50 observations and 4 explanatory variables, what can you say about autocorrelation if the computed DW values are 1.05, 2.50 and 3.97? So this, I think, should be very easy now for you to compute and understand. So let me just write it over here only. So the first thing is DL, which is 1.378, and then we have du, which is 1.721, 1.721, and then we have 2, then we have 4 minus du. So what is 4 minus du? It is 4 minus your du is 1.732, so 1.732 will basically be giving us 2.268, and 4 minus dl will be basically giving us 4 minus 1.378, and that gives us 2.622. So now let's have a look at the cases. D statistic is 1.05. That means over here. This is 1.05. So for case 1 it is positive autocorrelation is confirmed because D is lesser than DL. For sure. For the second case, it's 2.50. So 2.50 is basically lying between these two numbers, 2.50. It is between 2.2 and 2.6. So it is basically inconclusive on negative autocorrelation. So inconclusive on negative autocorrelation. And finally it's 3.97, which is beyond this, so 3.97. The third one is negative autocorrelation. That's confirmed. So these are your results from the DW test at 5% level of significance with the details that are given to you. So with this we complete question number 9. Thank you.